Well, my friends are all gone, but there's manicured lawns, and the people still think I'm a star. I walked around downtown, I met some fans on Lafayette. They said, tell us how to make it, cause we're getting real impatient. So I looked them in the eye and said, you don't wanna be high like me, never really know a guy like me. You don't ever wanna step off that roller coaster and be all alone. And you don't wanna ride the bus like this, never know who to trust like this. You don't wanna be stuck up on that stage singing, stuck up on that stage singing. I know, sad soul, Lord, I know that I know, sad soul, yeah. Stay gone. Sometimes you bend, sometimes you stand, sometimes you turn your back to the wind. There's a world outside every darkened door where blues won't haunt you anymore. Where the brave are free and lovers soar. Come ride with me to the distant shore. We won't hesitate to break down the garden gate. There's not much time left today. Life is a highway, I wanna ride it all night long. If you go in my way, well, I wanna drive it all night long. Through all these cities and all these towns, it's in my blood and it's all around. I love you now like I loved you then. This is the road and these are the hates. From Mozambique to those Memphis nights, the copper past have been Vancouver's lights. And knock me down and back up again. You're in my blood, I'm not an older man. There's no load I can hold. The road's so rough, this I know. I'll be there when the light comes in. Just tell me we're survivors. Life is a highway, I wanna ride it all night long. Woo. If you're going my way, I wanna drive it all night long. Gimme, 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 yeah. Life is a highway, I wanna ride it all night long. If you're going my way, I wanna drive it all night long. Let's go.
Ladies and gentlemen, please take your seats. Our program is about to begin.
Ladies and gentlemen, our program is about to begin. Please silence your cell phones or place them on vibrate.
أيها السيدات والسادة، سيبدأ البرنامج بعد قليل، لذا نرجو منكم التكرم بالجلوس في مقاعدكم.
This year we have speakers from around the world. So let's discover what we have today.
The true thing, the true strength is knowing your capabilities, knowing your limits, and still being true to yourself is a form of resilience.
Resilience means coping with the current threats of the very complex cyberspace, coping with the uncertain.
What I was hoping to share and hope to educate the audience is it is my point of view about resilience and examples that I have seen in my life.
It's very inspiring.
Amazing.
It was really good.
Hello, good afternoon, everybody, the resilient audience after all these days. It's my great pleasure to introduce Professor Eric Feron, my esteemed colleague in KAUST. He's a professor at the ECE programs/department. Eric has been 30 years in academia in distinguished places like the École Nationale d'Aviation Civile in France, Georgia Tech and MIT at the US, and is a fellow of the American Institute of Aeronautics and Astronautics. And very importantly, he's a very compelling speaker. I'm sure you're gonna love his talk. He will tackle two of his favorite subjects, system safety and robotics, in the scope, or what we can learn about it, in the scope of autonomous aerospace systems. So Eric, looking very much forward to your talk. The floor is yours.
Thank you very much, Paolo, for this very nice introduction. So yes, I am Eric Feron. I apologize, I cannot be on stage today due to a positive PCR test. And I am talking with you from Atlanta. That said, I think that today's presentation is a beautiful example of resilience, since my presentation is allowed to go on nevertheless. So today my topic is resilient robotics. I am Eric Feron. At KAUST, I work with the robotics, intelligent systems, and control laboratory. So let me go straight into a definition of resilience. From KAUST's Winter Enrichment Program webpage, it is the ability to withstand adversity, to weather challenges, setbacks, and unforeseen circumstances. The global pandemic has tested the resilience of people and systems the world over, but humanity has proven resilient in a time of exceptional adversity. And so it is with cautious optimism that the theme for WEP 2022 is resilience. Now, I looked at other sources, and one of them says, resilience implies an ability to cope with difficult situations, often creatively, whenever they are encountered. It implies that acceptance could be part of the solution. It is generally triggered by an event. It's a cognitive process, not a trait. It is generally thought of to aid well-being and health. And I believe that we should all congratulate ourselves and by doing pretty good in the world of resilience today. So I would like now to move on and give you a epitomization of resilience. Since my talk is about robotics, what is the ultimate resilient robot? To me, ever since I arrived in Saudi the ultimate resilient robot would be a man-made camel. Now, the camel is such a beautiful, God-sent animal that making a mechanical camel is close to impossible. The Quran says, do they not look at the camels, how they are created, implying a divine creature? And outside Saudi, people have recognized the beauty of the camel without even seeing them. For example, Sylvestre de Sacy says, will I share his vivid interest when he described all the splendor or all the signs of vigor and strength of the working animal that seems to have been expressly designed for the desert inhabitant by Providence. So that said, there have been attempts at making the mechanical camel. But more important, the camel has been discussed in many contexts as an enabler of resilience. For example, we find that publications talk about the role of the camel can be critical on household resilience to drought in pastoral and agro-pastoral households in drought-struck locations such as Uganda. It has been shown that having more camels means having more resilience. So the camel is resilient, it enables resilience. In other locations, in particular at KAUST, you can actually see a camel. His name is Shaheen, and he's right in front of building 20. I invite you to go see Shaheen, who is doing a beautiful job, not only being seen, but also, as you see, lending himself to the treatment, good treatments by the visitors. So another way of looking at the camel is from a business perspective. The camel has been used as an alternative to the unicorn in business. Unicorns are known to be fast-growing startup companies that quickly reach over $1 billion capitalization. In these trying times, the camel has been proposed as an alternative, enduring format for startup companies at a time of difficulty such as the one we're going through now. The author actually talks about camel resilience as the title of a book devoted to how we can go through the pandemic, by increasing our resilience. So, back to robotics. Where does the robotic camel exist? Well, the first possibility is in Star Wars.
Echo Station 3TA. We have spotted Imperial Walker. Imperial Walker's on the bridge. Echo Station 5-7. We're on our way. All right, boys, keep tight now. Luke, I have no approach vector. I'm not set. Steady, Dak. Attack pattern Delta. Go now. I'm coming in. blasters. Wrong group. Use your harpoons and tow cables. Go for the legs. It might be our only chance of stopping them. All right, stand by, Dak. Oh, Luke, we've got a malfunction in fire control. I'll have to cut on the auxiliary. Just hang on. Hang on, Dak. Get ready to fire that tow cable. Dak. Dak!
This video illustrates two things. First of all, the amazing adaptability of the camel that can live in the desert, both very warm and also very cold. This is probably one of the most adaptable animals currently living on Earth. The second point is that this video also shows some of my fascination for aerospace vehicles that you will hear about later in this presentation. So, are there robotic camels? Well, mostly representations. You can see beautiful artistic renderings of robotic camels coming from a variety of locations. However, none of these camels are real. So at this point, I would like to invite a real, almost robotic camel to enter the stage. And we're talking about Spot, the robot manufactured by Boston Dynamics and currently in development at KAUST. Omar, feel free to speak.
I don't know what else to do. What else? I don't know what else to do. I don't know what else to do, you know? I don't know what else to do, but that's it. I don't know what they're waiting for.
Let's go back. Let's go back. So, amazing demonstration of what Spot can do in real time, on stage, and without any backup. I am stunned. This is the first time I see Spot in action. You will notice, however, that the gait of Spot is not quite that of a camel, and it is quite worthy of investigation. So, going back to camels and robotics. Camels, and hopefully someday robotic camels, are extremely resilient. However, we must also realize that robotics helps camel activities to be resilient. What you see here is races taking place in the United Arab Emirates. Quite a while ago, the United Arab Emirates banned the use of children as jockeys for camel racing, which is an extremely popular activity over there. People's ingenuity has led to the creation of primitive robots who would replace kids in order to race the camels. At the bottom of this presentation, you see one such robot in detail, together with a whip that the robot is able to apply to the camel to speed the camel up whenever necessary. Therefore, robots and robotics can not only replace extremely resilient people, but today they can already help certain activities take place that could not happen without robots anymore. Let me bring another example of resilience, robotics, and camels. What you see here is the pattern of migration of the Saudi caravan as time goes on. Saudi caravans are caravans that surround camels, and the camels must move throughout the country according to the pattern you see here. From December to February, the caravan moves from close to here all the way up north of the country. Once the north of the country is becoming hot enough, the camels migrate again towards the south of the country and close to the empty quarter. They stay there till August, and then they finish their tour of the country by returning to their fall place near Mecca and therefore near KAUST. So how does the caravan work? Let's see that in the next transparency. So what you just saw is a caravan in motion. On the one hand, of course, the camels, sometimes several hundreds. On the other hand, a long series of vehicles carrying food, water, and lodging and fuel for all parties concerned, both humans and camels. Now, there are several challenges faced by the caravan today. One of them is safety. Caravans are subject to very strong winds, and sometimes when they are hit by storms, the caravan can be completely destroyed with loss of life. In other cases, the terrain is such that the vehicles are not able to stand up because they engage into slopey terrain which is made all the more dangerous that sand makes the stability of these vehicles quite precarious. With students Youssef Al-Mashti and Obada Wali, whom I want to acknowledge for their work bringing the first ever camel on campus today, we are working on developing robotic solutions to allow these vehicles to not face these problems anymore. In particular, for example, looking at solutions so that caravans and especially living quarters can automatically align with the wind so as to avoid suffering the kind of damage you see here. Another vision that we have is that today's caravan epitomizes the caravan of the old times, where the camel was the center of all survival in the desert. In fact, the camel and camel riding had been chosen as the primary and almost only means to transport goods throughout the desert as soon as a saddle system had been figured out. And at that time, wheeled vehicles had actually been abandoned. So wheeled carriage had been voluntarily abandoned by the Arabic community in favor of just these walking animals. Today's caravan is quite different. Involves wheeled vehicles. These vehicles consume power in the form of fossil fuels and are therefore far more dependent on outer supplies of fuel than their ancient counterparts. We are imagining in the future that the caravan could be heavily roboticized and work on alternate fuels as a way to recover the resiliency of the Saudi caravan of several hundred years back. So let's go back to resilience in the context of research. It is interesting to compare resilience and grit and to immerse these two concepts that are very close to each other, but very different in the context of computer science. We look back at the definition of resilience. It implies an ability to cope with difficult situations. It is generally triggered by an event, and it is generally thought to aid well-being and health. In the language of computer science, resilience is about safety. Grit is a non-cognitive trait that is constantly driving an individual towards a long-term objective. In the language of computer science, grit is liveness. And as such, we can, in fact, draw a fundamental and formal difference between resilience and grit. In the language defined by Amir Noailly, linear temporal logic, resilience means an accident will never happen to me. And it is written formally as a square followed by the sign not and followed by my state can enter an accident state. Formally, resilience can be verified, and it can be verified by means of a corresponding analysis of the corresponding automaton that drives the behavior of the state X. Grit corresponds to liveness. Liveness means I will eventually reach my goal. And there, the formal notation is a lozenge followed by my state belongs to goals, meaning eventually my state will reach my goals. As it turns out, liveness is a property which is much more difficult to verify. And so, since this WEP is about resilience, I will concentrate on resilience and safety for the rest of this presentation. So, where do we stand? Well, if we look at robotics research, and if we look at the general way we present our activities, those activities mostly reflect grits, meaning we have achieved a goal. You can see those, for example, in the editorial of journals, top journals in robotics research. On the other hand, resilience is much less talked about. Safety is much less talked about for a reason. A system which is safe doesn't make itself talked about as much. So in particular, if we talk about resilience, if we talk about safety, we're talking about serious business, which is not fun. And although people will not say it, the media tell us right away that it's when resilience fails that it is, I shouldn't say fun, this is an exaggeration, but interesting. You can see that on the front pages of several journals that I've picked at random over the internet. We see on the first left two front pages notions of safety failures with the ongoing pandemic. Then you see a safety failure again, but due to people's behavior on the Washington Post. And then again, safety failures in the case of the water scandal in Flint. In all cases, these represent breakage in resilience, and that break of resilience attracts attention. Let's be clear, all these activities here are not only there to inform people, but in fact to attract their attention. News that says that the system works well and that nothing happened are usually not in the front page of the journals. So where resilience works is, for example, aviation. We all fly, especially at KAUST, very often. Do we worry about anything wrong happening? No, we confidently board an aircraft thinking that the aircraft will fly us from origin to destination. And we are only very rarely reminded that each aircraft flight is in fact a miracle, especially takeoffs. And when we hear about the failures, they usually make, again, an enormous noise. Other examples where we hope we can create resilience. Nurse bots are becoming increasingly popular, and they are increasingly present at hospitals, including in Saudi. The mother of one of my students is already working with robots that support patients in her clinic. However, those robots are made safe by mostly moving slowly and doing very innocuous activities, such as carrying glasses of water or carrying other forms of goods, maybe information. Let me ask you, what would you think if this is the future of nurse bots? Would you let that nurse bot take care of you and give you your COVID jab? The answer is you would probably think a couple of times ahead before you let the robot do that. Not only that, but in this particular case, that robot is a unicycle, which is not necessarily the epitomization of stability. So for these kind of robots, again, we absolutely need to be sure that just like aviation, no accident will occur, that these robots are resilient to any kind of perturbations that could modify their behaviors in a way as for them to become dangerous. For that purpose, we have techniques and we have research activities taking place. We have solid design processes that have been inherited by years and years and years of failures trying to design industrial systems that are absolutely safe. We have, in the case of software design and verification procedures that we try and make as rock solid as possible. We also look at system architectures such that those system architectures are robust against all sorts of failures, including, for example, processor failures. Increasingly, we are developing here at KAUST and under the impulsion of Professor Palo, an awareness and the buildup of defenses against cyber attacks on these robots. Cyber attacks, in my opinion, and the ability to resist them is part of the resilience equation in robotics. To support all this, we have regulations, written documents produced by agencies and organizations specializing around these concerns. We have technologies such as, on the simplest case, requirements tracing, fault tree analysis, failure mode and effect analysis. And then on the research side, static analysis methods, very, very challenging, but already used in aviation. We have required and extremely important techniques that are simulations and testing. There is no way we can do without those. And finally, we have something I will talk about later, which is safety by design. We can engineer systems so that they are safe, even when the components that makes the technology, or at least some of these components, are unsafe. And last, at KAUST, we have education initiatives in system safety, robotic system safety, including a course that I offer every semester. The reason I can offer it every semester is the course is already recorded, it is available online, and I am looking forward to replacing the Georgia Tech picture by this picture whenever I can do that, and whenever we can perform a better job at ensuring caravan resilience by means of robotics. So activities that we are undertaking at the Robotics Intelligence Systems and Control Laboratory include system safety, robotic system safety. Now, in this picture, what you see is a large number of processors, all performing more or less the same thing, all networked together. And all these processors are there to ensure that the engine that you see in the upper left corner and the aircraft that you see on the screen, it's a simulated aircraft, keep operating and flying regardless of the failures that affect these processors. Each processor can be disconnected, broken, and the vehicle still flies. The difference between this setup, which admittedly doesn't look very much like a robot, but emphasizes a core aspect of the robot, is extremely different from what you see currently on most robots, where by and large, a single processor takes care of everything. And if that processor fails, the robot fails. This is changing fast. In aviation, 5 or 6 of these processors are kept running all the time and are organized in a redundant fashion, such that any processor failure is basically taken over by other processors such that activities, flying activities and control activities can proceed. However, these computers are very expensive and they provide reliability at a very high cost. Here we have 16 processors. And in fact, we could think about having hundreds of these processors that are much less reliable, much less expensive. Each processor costs on the order of $40 here. That would achieve the same level of reliability, of resilience for large and small robots. There is a motion towards achieving this kind of redundancy in autonomous automotive applications. Some of you probably remember Elon Musk showing how a Samsung-made computer was procured by Tesla. And Elon Musk saying, you can shoot through one of these computers and the car still runs. I'm afraid to say that only 2 computers is not enough. We need at least 3. And given the price of this computer, I would say we'd rather go for 10 cheaper computers than 3 expensive computers. Another activity relating to resilience that we are undertaking in our lab is safety by design. I gave it a name, Ariane. Why did I give this name? Well, the idea of safety by design is that the system that you're operating, a robot, operates by always keeping in mind how to get out of trouble. So the robot could be, for example, operated by artificial intelligence, but safety is ensured by forcing the AI not to think about the mission that needs to be performed, not to be driven only by the grids, but also it is asked to think a little more about, and if something goes wrong, I know how to get myself out of trouble. And the working principle of this is you trigger safety, not when you get in trouble, but when you realize that you don't know how to get out of trouble anymore. The name Ariane stems from the Greek mythology, whereby in Crete, the king Minos was the king. Ariane was his daughter. In Crete, there was this monster named the Minotaur, half human, half bull, that was locked up in a maze named the Labyrinth that was made by the architect Daedalus, the same Daedalus that would eventually manage to fly from Crete to Greece, while his son, who was not so wise, failed his flight because he went too close to the sun. Back to Ariane. A hero named Theseus came to Crete and heard about the Minotaur. At the same time, upon seeing the hero, Ariane fell madly in love with him. When she realized Theseus was decided to kill the Minotaur, she worked out a trick so that upon entering the maze, Theseus would be able to exit the maze as well, something that nobody had been able to achieve before. To do so, she picked a spool of thread. She gave the spool to Theseus, and she attached the end of the thread to the entrance of the labyrinth. And she told Theseus, keep the spool of thread with you. Unwind the thread as necessary. And once you have done your job, killing the Minotaur, you will be able to safely return out of trouble. So this is what Theseus said. His grits allowed him to eventually kill the Minotaur. The resilience that was built in by Arian allowed him to exit the labyrinth. Of course, the story doesn't tell what would have happened had Theseus run out of thread before he found the Minotaur and killed him. Embodiments of this philosophy are now studied in our laboratory for example, commercial formation flight. Commercial formation flight is a concept that has been present for about now more than 20 years. Everybody has marveled at the kind of environmental savings that could be achieved by formation flight by reducing the fuel consumption of aircraft without changing their performance, therefore mimicking what migratory birds do pretty much every season change. The point that our lab addresses is the one that was overlooked by everybody, which is, and what happens if the flight formation runs into trouble? How do we deform the formation? This activity will most likely have to be roboticized and made automatic. And we are currently studying this with one PhD student, Safa Saber, currently at KAUST. Another topic that we have been looking at, and which is very related, is safe drone path planning. This happened a number of years ago, whereby we made a demonstration of what we found out was an embodiment of Arian back then, whereby the robot, which was an unmanned vehicle, was commanded at a very high level by a pilot in an F-15, to be more precise, by a person behind the pilot in the cockpit of an F-15. That drone was commanded at the high level. The path planning was done by onboard artificial intelligence. Artificial intelligence of the time, it was very failure prone. That means that sometimes we would plan the path of the robot and the planner would return, I can't do it. How did we manage to maintain perfect safety despite the fact that sometimes the planner would fail? It is by doing what I said earlier. That is, by telling the planner, not only are you going to plan the trajectory, but first and foremost, you are going to plan for a few steps ahead of you, what we call a racetrack pattern. That is a trajectory that eventually loops around itself and that the robot can execute as long as necessary. As such, the robot was able to make progress along its desired path to embody its grids. However, because it always has a backup trajectory ahead of it, any real-time planning failure could be taken care of by entering the racetrack pattern anytime the path planner would fail. And the pilots thanked us for doing this because we were able, through that means, to keep the robot flying within the designated airspace. This airspace was very close to Los Angeles, and the pilots told us that on a couple of occasions, other demonstrations sent the flying drone over Los Angeles. So I want to finish this presentation by talking about not robot resilience, but again, robotics for Red Sea and oceanic resilience. There is a marvelous laboratory here at KAUST that focuses on coral restoration. In fact, there is more than one laboratory. We have the Red Sea Research Center on the one hand, and as part of the Red Sea Research Center and surrounding activities, we have many coral restoration activities based on studying the biology of corals and also creating conditions favorable to coral regrowth. And one activity I love a lot is led by Professor Charlotte Hauser and involves robots building substrates for coral to eventually redevelop on the floor of our beautiful Red Sea, in particular, and oceans in general. Thank you very much for your attention. I can take any questions at this point. By the way, yes.
Hey, hey. Thank you, Eric. That was very nice. And we have some time for questions. So we have some questions. Okay. We have some questions from the audience that just came. All right. So, Eric, there's an interesting question which talks about these resilient robots which can provide service to the community. They could also be used as war machines. And so is there anything within the scope of the robot architecture, not excluding laws and other, is there anything that would prevent resilient robotic research from being exploited by adversaries?
So thank you, Paolo, and thank you, dear viewer, for this important question. Every technological improvement is like the semi-god Janus. It has two faces, a nice face and an ugly face. It is extremely difficult to prevent new technological developments, not to have military use. There are ways to prevent robots to be used in a military way or in a dangerous way in general. For example, pick the small scooters that are present now all over the planet for people to move through the city. These scooters are now subject to geofencing. Geofencing allows these scooters to go fast in areas where there are low probability of collisions with, say, pedestrians, and are limited in speed wherever those scooters are used in an area where the density of pedestrians is high. Likewise, it is possible to geofence vehicles of all sorts. Other mechanisms can be, and of course, by the way, geofencing and making sure these vehicles cannot behave the way we don't want them to behave requires the ability to withstand break-ins, okay? And that is where cybersecurity plays a very important role, because we need to make these machines impervious to outside attacks, outside attempts to break in those systems and modify their behaviors. Many of the flying drones that we have now are already equipped with protections against breaking in, and many of these vehicles operate all the way down to the heart of their guidance using encrypted signals. That said, there are limits to what we can do, and this Janus god that appeared thousands of years ago is likely to remain in our imaginations for the time being.
Thank you. There is also an interesting question about social issues, which is with technological advances in robotics, many people feel their jobs will be in danger. So what is your opinion? To what extent the explosion of robotization will endanger the job ecosystem?
So I would like to borrow from a presentation that was given to us at KAUST by Professor Schmidt-Huber. That was about 2 months ago. The same question appeared, at least in my mind, and many other people's mind, about AI taking over human brains and eventually expanding to take over the universe. I believe that, well, this is an asymptotic direction that we're aiming at. However, tomorrow is not the day when that happens. I'm also intimately convinced that connecting intelligence with what I call the real world, that is the world of physical artifacts, is an extremely difficult task where the human is going to remain for a very, very long time. Why? It suffices to look at all the systems, all the things we do today. The robot is very, very far from me being able to achieve all the things we do, not only to achieve them, but achieve them fast and safely, like humans are able to do. Who says physical world? Says physical accidents, loss of life. Robots will be held to much higher standards than humans as far as failures and loss of life and loss of goods are concerned. And why is this? Humans are free to do a lot of things. With freedom comes responsibility. Humans can be put on trial. Intelligent robots will have much more trouble being put on trial, and whole companies will be involved. The kind of challenges that will be faced by the robots and these companies in terms of legal problems whenever loss of life happens will be much larger than the problems faced by a single human who misoperates a single system. The debate, of course, can go on for hours and hours, and I don't claim what I just said is a perfect answer, but I hope I have raised enough issue to convince you that the human is not going to be gone out of the loop, if I may say, anytime soon.
Thank you. Please, audience, if any of you feels like asking a question, please approach the microphone and I'll be seeing you. Redundancy, so you have suggested redundancy as a means to improve safety. And you have also mentioned then, classic cybersecurity protection mechanisms. Could that kind of redundancy, for example, be used not just for accidental threats, but also for attacks, given that the classic cybersecurity protection mechanisms have been failing on us, as we have seen, for example, in autonomous vehicles?
So I believe that redundancy may be used for cybersecurity. However, I am not a full-blown specialist on these kind of issues, and you probably have a much better answer than what I can provide. I can only remember one person saying, well, let's run a few computers a few seconds behind the computer in charge, if I may say, such that if the main computer runs into trouble, then we can use the computers that are running behind, artificially behind in time, can then fast forward to the present without taking the data stream that the main computer got and take over the operation of the vehicle. That suggestion was made to me by a person who now works at the Georgia Tech Research Institute. I do not claim that it is the only solution, but it probably offers a possibility.
Thank you very much. Okay, so let's wrap it up and thank Eric once more for his presentation. Thank you very much.
Thank you very much, Paolo.
Thank you. And the session is adjourned. Thank you very much.